Ever stop to think about why things move the way they do? Why does a gentle push send a small ball rolling, but it takes a mighty shove to budge a boulder? What unseen forces are at play in everything from the gentle sway of a tree in the breeze to the immense power of a hurricane? We experience these forces constantly, intuitively understanding that pushing or pulling something can change its motion. But have you ever wondered how we actually quantify these interactions? How do we put a number on the oomph behind a push or the tug of a pull? For centuries, philosophers and early scientists pondered these very questions. They observed the world around them, trying to make sense of the seemingly chaotic dance of motion. Ideas were proposed, debated, and sometimes discarded as new observations and experiments came to light. It was a slow and often frustrating process, a gradual chipping away at the mysteries of the physical world. Think about it. Before the advent of precise measurement and a unified theoretical framework, understanding motion was largely based on qualitative descriptions and everyday experience. There was no universally accepted language to describe how much force was being applied or how much inertia an object possessed. Imagine trying to build a complex machine or predict the trajectory of a cannonball without a clear understanding of these fundamental principles. It would be a matter of trial and error, a process fraught with uncertainty and potential failure. The need for a more rigorous and mathematical approach became increasingly apparent as technology began to advance. Scientists sought a way to move beyond simply observing and describing motion to actually predicting and controlling it. Enter the 17th century, a period of intense intellectual ferment and scientific revolution. Across Europe, brilliant minds were grappling with these fundamental questions, building upon the work of their predecessors and daring to challenge long-held beliefs. It was a time of groundbreaking discoveries in mathematics, astronomy, and physics, laying the foundation for our modern understanding of the universe. Thinkers like Galileo Galilei had already made significant strides in understanding motion, particularly the concepts of inertia and acceleration. His experiments with falling objects and inclined planes challenged Aristotelian physics and paved the way for a new way of thinking about how things move. But it was one towering figure who would ultimately synthesize these ideas into a comprehensive and elegant framework, providing the very definitions we're about to explore. A man whose name has become synonymous with scientific genius, whose laws of motion and universal gravitation would forever change our understanding of the cosmos. We're talking, of course, about Sir Isaac Newton. Now, when we talk about Newton, the first thing that likely comes to mind is the famous story of the apple falling from the tree, sparking his realization about gravity. While the romanticized version of this tale might be a simplification, it captures the essence of Newton's approach, observing the everyday world with a keen eye for underlying principles. He wasn't just passively observing, he was actively seeking patterns, formulating hypotheses, and rigorously testing them through mathematical analysis. But the Newton we're focusing on today isn't the man himself, the brilliant mathematician and physicist. Instead, we're diving into the definition of a Newton, the unit of force in the International System of Units, SI. So, what exactly is a Newton? At its core, a Newton, symbolized by the capital letter N, is a measure of force. But that simple statement doesn't really tell us much, does it? To truly understand what a Newton represents, we need to delve into Newton's second law of motion. This fundamental law states that the acceleration of an object is directly proportional to the net force acting on the object and inversely proportional to its mass. Mathematically, this is expressed as the iconic equation F equals ma, where F represents the net force acting on the object, m represents the mass of the object, a represents the acceleration of the object. This equation is the key to understanding the Newton. It tells us that a force can cause an object with mass to accelerate, meaning to change its velocity, either its speed or its direction. A larger force will produce a larger acceleration for a given mass, and a more massive object will require a larger force to achieve the same acceleration. Now, let's use this law to define the Newton. 1 Newton is defined as the force required to accelerate a mass of 1 kilogram at a rate of 1 meter per second squared. In other words, 1 N equals 1 kg/s. 2. Think about that for a moment. This seemingly simple definition encapsulates a profound relationship between force, mass, and acceleration. It provides a precise and quantifiable way to measure the strength of an interaction that can cause a change in motion. To make this more tangible, let's consider some examples. Imagine holding an apple in your hand. The Earth's gravity is pulling down on that apple, exerting a force on it. If the apple has a mass of roughly 0.1 kilograms, about 100 grams, the force of gravity acting on it is approximately 1 Newton. So, when you feel the weight of that apple in your hand, you're experiencing a force of about 1 Newton. Now, imagine pushing a shopping cart. The force you exert on the cart causes it to accelerate. If the cart has a mass of, say, 10 kilograms, and you want to accelerate it at a rate of 0.5 meters per second squared, you would need to apply a net force of. So, you would need to push with a force of 5 newtons to achieve that acceleration. It's important to distinguish between mass and force. Mass is a measure of the amount of matter in an object, a fundamental property that resists changes in motion, inertia. It's measured in kilograms, kg. Force, on the other hand, is an interaction that can cause a change in an object's motion. It's measured in newtons, N. While they are related through Newton's second law, they are distinct concepts. Another common point of confusion is the difference between mass and weight. In everyday language, we often use these terms interchangeably. However, in physics, they have very different meanings. Mass, as we've discussed, is the amount of matter. Weight, on the other hand, is the force of gravity acting on an object's mass. It's a force, and therefore it's measured in newtons. The weight of an object depends on both its mass and the strength of the gravitational field it's in. For example, an object with a mass of 1 kilogram will have a weight of approximately 9.8 newtons on the Earth's surface, because the acceleration due to gravity on Earth is about 9.8 meters per square second. However, the same 1 kilogram object would have a different weight on the Moon, where the gravitational acceleration is much weaker. Its mass would remain 1 kilogram, but its weight would be significantly less. The concept of the Newton is fundamental to many areas of physics and engineering. It's used to quantify all sorts of forces, from the gravitational force that keeps planets in orbit to the electromagnetic forces that hold atoms together. Engineers use the concept of force, measured in newtons, to design structures that can withstand various loads, to calculate the thrust required for rockets to escape Earth's gravity, and to analyze the stresses and strains in materials. With that said, thanks for watching, and until next time.